Yeah, so today we speak about recommendation system. We have several places where you can ask the question during the webinars. First, it's Slando. We will try to use it for collect all your questions, and then after a presentation, we'll answer to them. And also, if you want to participate in live discussion, please join to our Zoom, and we will discuss and give you a microphone so you can ask the question live. Also, under the video, we have links for donation. Please donate and help us raise more money for Cola. And after the webinars, we will publish the video, and also you can find Dora and all our speakers in Slack channel. So join to the Slack channel as well. So for now, I give the microphone to Dora. She is a senior data scientist at Metro.digital, and she will share with us her expertise in building a recommendation system on which she working last several months, as I understand.
Thank you. I'm going to share my screen.
Yeah.
Hope you can see.
Yes.
Okay. Thank you, Dmitry, for the introduction. Also, thank you, everybody, for joining the call. I hope you can hear me well and see my screen. I hope we raise as much money as possible for this great cause. And I want to also thank Dimitri's team for making this possible, and the time and the effort spent making the webinars and organization around it. I'm really excited to be talking about this topic. It's how to build a recommendation system from scratch. This was the latest project I've been working on with my company, and yeah, really excited. So I'd say we start straight away. Imagine you there sitting in a cafe, drinking coffee, and you're looking ahead at the weekend. You're getting ready to this great dinner you organize with your friends. You want to surprise them with your cooking abilities, so you obviously head to the Metro website searching for the tool you are missing. Is this cooking mixer? You already start to feel it into your hands just to realize it's out of stock and you can't buy it. Too bad. In a fraction of a second, you will be heading to a competitor's website. What you didn't probably know at this time is that there are about 50 types of different cooking mixers in assortment. Many of those are actually available at this time. And you needn't know this, but that's totally okay. Because what is missing in this story is an alternative-based recommendation system. It will be there, displayed on the page, ready to drive you to the top replacements which have been selected for you. You might even discover a type of mixer you didn't know existed, even better than the one you were searching for. And on the other hand side, the company will make a purchase. And this is a win-win situation. My name is Dora Petrella. I'm a data scientist at a company called Metro.digital, and I work in a team that is focused on exactly this kind of problems, building recommendation systems like this one from scratch, also based on different logics, using the Metro data. I was really excited to be talking here today at this webinar, and I asked myself, if I were sitting right there where you are right now, what is it that I would want to learn or know? And when I answered myself that it would be probably the learnings, how the project evolved from this latest project I've been working on. So what did I learn myself working as a data scientist for this project? What were the pitfalls, the challenges? How did it develop? What should we not do and what should we do? I also prepared a short demonstration at the end of the call. So yeah, I'd say we start from the beginning. just like you saw yourself in the shoes of a cook and you had to make this great dinner for your friends, I also see myself sometimes as a cook. I am given a goal, a final project, and I need to put together ingredients, come up with a tasty recipe, and deliver the best flavor to our customers. So before we start going into the details, I have to give some context around what the company actually does. And this is like the kitchen. This is like the place where things happen. And all projects are possible. So Metro.digital is an IT company. It builds software for the wholesale metro. And so data comes from the wholesale metro, guess what? And this kind of data, they come from a card that our customers receive at registration time, at least some kind of data. Customers are businesses themselves, so this is a business-to-business scenario. They might be restaurants, kiosks, hotels, even big hotels, 5-star, caterers, offices, and all of them are very heterogeneous. This is what it distinguishes a B2B from a retail, for example. They don't behave all at the same way. Many of them need different kind of products than others. Many of them are kind of bigger or smaller based on the amount of orders and the quantity of products that they consume. So products, on the other hand side, they go from food to non-food, but with a very strong focus on professional items. So even when we speak about non-food, it's professional cooking tools, there is specific clothing, even specific shoes for working in a kitchen, or barbecue, but also big decorations. There is even a big giant cat, tall 1 meter, that I personally encountered one time, and I asked myself, is people even buying this? So yeah, customers are businesses, products have to serve our customers in the best possible way. Data come from this card. This card gives us big advantage with respect to the retail world in a way, because not only we have in our database information what is people buying and when, but even who is buying. So the customer might be located in a certain place. It might be an Italian restaurant versus a German or whatever other country. Stores, on the other hand side, are in 22 countries worldwide, and in some countries, the business more active, in some others is less active, let's say. Also online data. So like you can imagine, there is a website, there is an app. So from all of these touch points, we gather information whether people is adding to basket or not, click events, search events, and so on and so on. This is all great material for a data scientist to head into the kitchen and start working. And just like a cook has to find its best ingredients for the next tasty recipe, I had to do the same thing. And for these particular projects, I was not only taking care of the data science part of it, but also some requirement collection. So I had to talk to the people involved, understand what we need to achieve, what this recommendation system should look like. So in this phase, I talked to a lot of people and I asked the basic questions. Where are alternatives being hosted? So what is the final end goal for this recommendation system in the end? And well, this was straightforward. The people had a clear idea in mind how this should look like. We have a web page and the user is viewing a product, but unfortunately this product is out of stock, just like in the mixer I displayed in the beginning. There is a button, show me more, give me some alternatives. And when the user clicks on this button, a pop-up window displays alternative products for it. So possible replacement to the out of stock item. Now suppose the user added also to cart. This is a second place where alternative recommendations are triggered. Maybe the user got back to the basket in a second, at a second point in time where the product is now not available anymore. So right here, again, the same button, we click on it and we see some recommendations displayed. Not only that, there are more places where alternatives are needed within the company. There is an entire team working with problematic orders. So they see a UI or user interface that looks like this. Orders come and pop up that are problematic. Maybe there was a wrong package, maybe there was mistakes with the delivery or whatever other reason. Now this needs the attention of an employee. The employee will see a problematic article, click on it, and now it will be at the customer at the phone with the customer and asking, would you like to replace this item with another one? So at the moment, it is done manually at the beginning of this project, at least. Why not displaying the same pop-up bar that we saw earlier, when the employee can get support and better serve the customers? Not only this, there is also an entire team taking care of the listing decisions. There might be problematic contracts, prices issues. Maybe there might be the need of thinking, shall we delist from assortment a certain type of item? In these situations, it's very tricky because we don't know upfront whether revenue will stay the same or not. So for this type of employees, by the way, there are also data scientists in there, it might be beneficial to know upfront whether there is a replacement for any given product. And so also internally, employees might benefit from knowing what are good alternatives for any given product in assortment. So, okay, I had talked to the teams involved, understood what we want to achieve. I also understood what are the difficulties already. What is the definition of a good alternative? I asked this question to a lot of people, and unfortunately, there is no great answer to this question. Why? Because for some customer, a good replacement for a wine is another wine in the same brand. Maybe for a different customer, it's not, and they want to stick to the same price or the same quantity. So there are a lot of variables that play into this game of alternatives, and even experts in category management could not agree what is a good alternative. So that it's part of challenges that we need to keep in mind when starting with a new project. But okay, I had talked to the people, I had gathered a lot of information. We sat together with my team to collect requirements, so the ingredients for this recipe. The first one is definitely flexibility, because we're speaking about serving different customers, like serving also employees, and they have their custom logic on top. If some of you work with online machine learning, you might be familiar. There are some set of rules. Not everybody can view all pieces of assortment. Some customers can get delivery, some customers cannot. So our website want to be, say, able to apply custom filters on top of the recommendations, which means this recommendation list must be very long. Quality. That's true for every recommendation system, but in this particular scenario, there were complaints about an existing recommender system, and I had to dig and understand why and what is good quality, what does it even mean? Low latency here, recommendations have to be fast, in milliseconds, we want to be able to deliver. Why? Because users lose their attention very easy. If content is not being displayed fast, they very easily go in somewhere else, and we lost the opportunity. I can spoiler to you that we will be tested for 1 year a different recommendation system and discovered that latency is the main driver of online metrics such as click-through rates. They play a very big role. Low recommendations are very harmful in this situation. And coverage. Now, this will become clear in a moment. Coverage means to us how much of the assortment can we actually cover with recommendations. So what is the percentage of articles that actually receive some kind of alternatives? We wanted to improve coverage, but this will become clear in a moment. Again, there was an existing approach, and we will go to it. Automation as an internal requirement to my team for the way we work. Because we're focusing on recommendation system, we have other recommendation system running already in production. We want to minimize the amount of manual effort that we make. We want to automate the whole process from data generation to building a machine learning pipeline, training and serving recommendation. We just want to have alerts such that we know when it's time to make a manual intervention, but we don't want the whole process to be entirely manual. And for this recipe, we have a cooking time of 6 months. That was estimated from ourselves in combination with our stakeholders as a deadline for this project. Okay, and everything's understood. We have our ingredients, and now it was time to head to the next phase. We have to start researching. And now here I felt myself just like this old woman selecting blueberries. She is there looking around, what is available, what is the best that I can select to deliver the flavor I want. In this situation, I'd say for a data scientist, what is important to do, which many of you for sure know, is to read a lot of literature around the problem. What are common approaches to solve this problem? What are limitations of the common approaches? Do I even fit all of my requirements? But in my scenario here, I also had to understand what the system that was already running was doing in the first place, because it was already a recommender system being used right there. So that's what I did. I asked around my colleagues and the people involved, what is this recommendation system doing? And I discovered an external consultancy firm a few years ago had developed a recommendation system to solve this out-of-stock problem. But it was actually developed for assortment-related issues, not for being displayed online. Then later on, it was, again, business context. We have cost, and we have cost coming from people and cloud and time spent. So some manager at a certain point thought, why not? We can even reuse it online. And I have nothing against this approach, as it serves as a very good starting point for us to do better. Jules was a statistician from Britain. He invented a coefficient of association. There are out there many more variations, but there are many coefficients of association in statistics. This is one. He didn't invent a recommender system. He invented this formula specific that was then used and adapted to be used to serve as a recommendation system. This is not a machine learning based approach. Again, this is a formula invented by a statistician. But how does it work? So we say goodbye to George Jules, and we make a tiny example just to get an understanding around it. We imagine that we have two products, an apple and a candy. And now we collect data around how customers interacted with these two products over a time of 2 years in a country. Now, let's not forget the company operates in 22 countries. So we consider we consider all customers and all of their in-store transactions. Now we will have some group of customers, we call it A, that are interacting with both products, but never in the same basket. And now suppose that these are 150. There will be some customers who interact with one, but not with the other. And now suppose also that we have a total of 500 customers, but this is now a toy example and the numbers are totally made up by me. Now, just like we did always in school, we need to plug these values, A, B, C, and D into this formula. And what we get back out of it is a score. This is the value of the coefficient of association between X and Y. Now you have to imagine this at scale, repeated for a lot of products, repeated for all countries, and we come up with a lot of scores that are matching pairwise combinations of articles. We have in this situation a score of 0.2, which is near 0. So the rule says no association. So most likely these two articles are not alternatives to each other. Okay, makes some sense. When is it likely that two products are alternatives? If A is big. So this A, we can think about it like a group of customers who kind of think or behave in a way that these two products can be alternatives because they never purchase them together. They interact with both, but never together. So we want this number to be very big for a score to be high. And we want the other customers that are not behaving like that to be in a small number. Also, for the way this algorithm was implemented by the external consultancy firm, we have an empirical threshold of 0.8, and we say we only consider scores that are greater than this value to be confident enough that we found some alternatives. This was implemented in SQL and automated in Airflow to run automatically, essentially. And now as I'm speaking, you start to picture most likely what are the main limitations and why we need to replace it. For a lot of products, we don't unfortunately find any alternatives by following this methodology. Why is that? Well, because we need a lot of transaction for this rule to work out and say that two products are alternatives. If a product doesn't come up with a lot of transaction from customers, we don't have any alternative for these ones. So we have a low coverage. We have a value of 40% estimated for Germany, for the Germany dataset. And we want to improve that because it means that most of the times we don't display anything online. This also comes from the fact, again, this was reused. It was developed for a different problem and then taken and used in an online scenario. So it doesn't consider, for example, online data. It's only using in-store transactions. And where is quality lacking the most? So, by the way, these complaints come from people who internal to the company from different angles. They reach out and they say, hey, these alternatives don't make so much sense. And fast data analysis around it shows that quality is not sufficient, again, for low transactional items. They are most of the time non-food. So think of a fridge, think of a printer, think of a phone. You buy it one time, but really for the nature of this kind of articles, you don't get to it again, or yeah, they just don't receive so many transactions like butter or flour or other type of products. So here is where this assortment requirement is coming from the existing methodology. People was just not happy with having so little. So scalability here is something we need to reach. And I learned by observing what's existing, that was a major problem. But this is not enough right now. We need to go out there and do further research around what are common problems to solve this issue. I read a lot of papers, but I also went through the company's websites, say Amazon blog, I read Instagram recommendations, I read about YouTube's recommendations, because definitely we are not at all comparable to these companies with the amount of data that we have and the amount of expertise. However, it's always good, I think, to compare academia research to real world existing methodologies and then find a compromise that fit all of the requirements that we need. With my very big surprise, I found the most common algorithm to be named as being used in production at real world system being a variation of word-to-vec, the year-old word-to-vec that I had studied at university. And now I'm imagining that many of you exactly know what this is, because I know that there are a lot of ML professionals in this round. However, there might also be people who is not so familiar. So I thought it's a good idea to do a short recap around it. Word2Vec is not developed, it's not born as a recommendation system. This is was coming from a paper published in 2013 by the Google Research for NLP related problems, so natural language processing. This is an algorithm that works with text, and in my scenario, we have nothing to do with text. Text in my scenario, it's even very unreliable, and we don't use it for machine learning. So how to get from recommendations to Word2Vec, it will be clear in a minute, I promise. So just for the people who is not familiar, I'd say just 2 words around Word2Vec. This is very, very popular algorithm, again, introduced by Google Research, that it comes with 2 implementations. One is the skip-gram model, and one is called the continuous bag of words. In text mining, the main difficulty is computers don't understand text natively, or it's not so straightforward to make a computer understand semantics and meanings, just like we humans do. At the base of this algorithm, there is an assumption. It's called the distributional hypothesis. Words that appear in similar context share some kind of degree of, they are related to each other, and therefore they share some similar semantics, so some similar meanings. And this is intuitive. If we consider a lot of text, suppose the Wikipedia pages, and now we are looking into a topic, say, I don't know, philosophy. We talk about Kant and Hegel most likely, but we will not most likely speak about, I don't know, the Queen of England into this scenario. So based on this distributional hypothesis, we can try to measure those similarities going from a sparse scenario to a dense one. But now it looks very complicated, but I try to make it as simple as possible. Suppose we have sentences like this one. The quick brown fox jumps over the lazy dog. The basic idea behind the skip-gram models is to build a pairwise combination of words, giving a target word. The blue highlighted cell here is a target word. We look at context, some context around it is this window box, which is around the target word, and building simply all of the pair of combination of words. These are called skip-grams. And they are training algorithms that are being fed to the Word2Vec model. I have here at this link source. It's a blog, very, very simple, step-by-step explanation of the skipgram model from which I stole the images. I recommend it to the people who might be interested or want to have a refresh around it. Okay, but now again, I'm speaking about processing text. I'm speaking about skipgram. What does it have to do with alternatives? Well, I can tell you that we can cross out this name, replace it with Word2Vec, and this is being used as, I'd say, one of the most common ways I've found to solve my same problem. So identifying replacements. But from going from Word2Vec to Prod2Vec, we need to make some changes. One word is one article ID. And one sentence is one user session. So instead of looking at sentences, we look at user session. A session started by a user may contain a ordered series of articles that the user is browsing. And these articles are linked together by this co-view event. So they are viewed within the same session. And now we consider a target item, and now we consider a context around it. And we slide this window over the session, and we then build our skipgram pairs. This is the basic idea behind a model called Word2Vec, this machine learning algorithm. And I have linked the paper to this at the end of the presentation. Okay, cool. But what is the algorithm doing? Many of you, I'm sure, know Word2Vec. Again, let's remember one word is for us one product ID. Because we're speaking about product recommendations and we don't use text in my scenario, in my company, for doing machine learning. It's just not reliable enough. The Word2Vec algorithm is a simple neural network where we process input vectors, which in theory are one-hot encoded. Why do we say this? See, a number here, 10,000, is the size of the vocabulary. So for me, it's the size of the assortment that shows up in the training dataset. Then this is having a value of 0 except for the position of a given word, so a given product. And now we have this is a neural network now with one hidden layer, and there is no activation functions. This hidden layer serves as a lookup table. This is the basic idea behind it. But again, in the blog I linked, you find a very in-depth walkthrough where it's explained step by step so easily. These circles are neurons. We have, this is a matrix, the one in the middle, and it has size 300 in this scenario times 10,000. So it's the vocabulary size times a hyperparameter called embedding dimension. Is 300 in this case for the tiny example. The output layer is there to output probabilities. And we are looking at the probability that for any given word, this is also of size 10,000, we have a high probability that this word belongs to the same context as the given word. This is for the skipgram scenario. There is a different implementation, but I leave it off for the moment. The hidden layer is what we're interested in. The basic idea is that we want to return this layer in the middle and disregard the softmax classifier. We only use it to update some values, they're called weights, via backpropagation, and we are interested exactly into this matrix, which is here. In the beginning is initialized at random, and then over time, as the algorithm is learning, weights are updated, and this is what we want to return. What is this metric doing in the end? By the way, the update is done by minimizing a function. There is a cross entropy loss. I say these things just for completeness. And the true labels are, so the driver of this, the whole process are co-view events in a scenario. Well, we get back out of this a vector for every word, in the case of Word2Vec, for every product, in my case, in the Prod2Vec example. So every product will be associated with a vector with a certain number of entries. Okay, you are all asking yourself, okay, many of you, I'm pretty sure know this very, very well. The main advantage of these vectors is, okay, now you have a vector for every product in assortment, imagine that, and you can match them. Any given product can be matched to any other. And what we can do on top, we can measure distances. The closer the distance, the more similar products are to each other. And at the end of this presentation, I will also show you how these vectors work in our scenario. So what we do, yes, we measure distances just like by a cosine similarity, very simple. And we get back for a product a sorted list of alternatives that is as long as the number of remaining products in the training data set. So as I'm speaking, you can now imagine what is the main benefits of this approach. Here, when I'm speaking now only of the research phase of this project, so I just was brainstorming together with the other data scientists in my team, what were the benefits. Definitely, it's a scalable approach. So remember, we want to have a better coverage than the existing one. And this kind of methodology comes with a very high coverage. Like we can, for every given product, we can match it to any other. Sure, as far as we get, the more quality is degrading. However, it's still scaling. Implicit feedback is also a benefit because we don't have a real ground truth around alternatives. We don't have a real source of a product is a replacement to another. So we let data tell us what is a good replacement in the end, inferred from users' behavior. It's relatively easy to implement. I say relatively because yeah, it depends. There are a lot of implementation available. The algorithm is so famous, like the data science community developed highly optimized versions of it that also, even with GPU support or that with low training time, and it's so easy to kind of implement, let's say. Also fits very well the current tech stack. This I liked because we have other algorithms in production and we have another algorithm already running in production that also is based on a similar logic. So our tech stack was really, say, prepared for hosting these kind of vectors. And it can be personalized. I heard from stakeholders that the need for personalized alternatives such that every user see a different alternative would be desirable in the future. And this kind of methodology could be adapted to a personalized algorithm with easy tweaks around these vectors. What is the main limitation? Definitely the cold start problem. You won't be able to have a vector for a product you have never seen before. This is, however, only a limiting downside in my scenario, because again, we have another algorithm that also suffers of cold start, and we already had implemented some fallback logic. So that's why I say that the tech stack is kind of prepared. Retraining frequently, or maybe try to derive this vector from the others. This is another possibility, or having a fallback to a baseline. This is another way. So cold start can be mitigated in some ways. So it was not my main concern. However, prone to popularity bias was a major problem. This algorithm is not using any feature. It's just relying on co-view as a way of identifying alternatives. And like you can imagine, some products or few products will show up a lot, and a lot of products will show up very seldomly. So we can expect quality to be really good for a bunch of products that everybody like to buy or they need, and less good for others. And unfortunately, I also experienced this behavior because it's part of collaborative filtering in many cases before, and it's very bad. There is a famous paper that I also linked at the end, where authors investigate on the business value of recommendation system, and this phenomenon of being, we are users ourselves. We look at recommendations, we see a bad example, and we make judgments on the overall system. That's very, very common. And yeah, I didn't want this to happen because a lot of our products are actually unpopular. One word is worth spending. The authors of Word2Vec came up with 2 improvements on top of this basic skip gram model to mitigate the issue. One of them is a sampling table, for example. But I don't want to spoil too much. We tested it and we found a better way. So I and the data scientists which were working with me asked ourselves, is there anything better we can do even before we start trying out things? And yes, we discovered a new version of Prot2Vec. It's a different paper called Meta-Prot2Vec, also referenced at the end, which was very promising in our situation because we have a time constraint. We are not free to investigate as much as we like, definitely. This Meta-Prot2Vec is a variation of the Prot2Vec algorithm, which is based on a very simple idea. We know something about our products. We know what some drivers of alternatives are. Why not just giving it to the model? That's it. That's the idea. So we know, for example, that the brand, the category, the subcategory, they are all drivers of alternatives. And we can, in fact, concatenate this information together with the given product to help a model improve, especially on those products that are seldomly bought. Why? Because maybe that the product is sharing some other properties to other products which are in fact available, that are in fact popular. So they share the same category, maybe they share the same brand, and this is supposed to help quality on those long tail items. So exactly the main point we were so concerned about. How does it work? The algorithm stays totally untouched. Training works exactly the same. We just need to provide more output pairs, and we need to make a tiny modification to the formula for the window size, but that was very easy to do. And we can include as much metadata we like. So now the model becomes a model with features, something that was not possible in the basic Prot2Vec version. Okay, so we were pretty much happy to try this out. Why? Because we wanted to test CBOW versus skipgram for the Prot2Vec implementation. Prot2Vec versus Meta-Prot2Vec was already comparing all of this to JuiceQ. It already started to feel a lot of work, and we had to start implementing something. So this was time to end research, start to get our hands dirty. Now again, all of you might think, yeah, there is another approach. Yes, there is many other approaches. There is a lot of complicated models, deep learning, whatever you like, you name it. However, we just needed to get some version 1 for this algorithm that would be better than the JuiceQ recommender, prove that it's working, maybe A/B test it. And then version 2 can be a complicated model, a little bit more than this one, but that will come after we have observed how users like it. So that's why it's so important to be fast at implementing, and that's why we were satisfied with this research. Time to get our hands dirty, we get into the kitchen and we start building something. How we work together on implementing recommender system within my team. We have data scientists are responsible for building machine learning pipelines. ML engineers are there to support with very technical issues. They also build APIs for our recommender system. Every recommender system comes with an API. What I said about the tech stack earlier, that's fitting very well, is because we had already an Elasticsearch as a tool there, ready to serve vectors from a different algorithm. So it was fitting well for this reason. We use Google Cloud Platform, and this is a product from Google called Vertex AI, which is a product from Google that allows data scientists to very easily head from a prototype to a productive pipeline. They try to make it as simple as possible to be pipeline on the cloud. And this was the first time we as a team tried out this way of building pipelines. Before we were using Kubeflow, which is also from Google Cloud. It was very easy. I can confirm that pipeline is built within a notebook, like a Jupyter notebook. But we built components that look like this square that you see here. They are Python code under the hood. And we tried to build components that are as much reusable as possible, also for new recommendation system to come in the future. So we want to minimize as much as possible the delivery time from idea to production. That's why out of every component, by the way, the pipeline caches the result every time we rerun it again. So we don't waste too many resources. The Vertex AI comes also with hyperparameter tuning on the cloud. We implemented it as one training dataset per each country. So we have 22 trainings separately, one per country, and we gather all of the whole data is gathered per country. This big query sequence generator is just gathering all of those sequences, then we pre-process and so on. We use also MLflow. This is an open source tool which comes at handy when we want to make experiments under different variations of algorithms. You know, you remember I mentioned we tried CBOW, skipgram. By the way, skipgram was much better. We tried Meta-Prot2Vec versus Prot2Vec, different variations with different combination of features. Yeah, we encountered a lot of problems. We had to regenerate the data set many times. MLflow helped us doing comparisons, so comparisons between all of these runs. By the way, I also forgot to say, we tested a Python implementation and a TensorFlow implementation. Takeaway out of that, TensorFlow is better because it comes with, it's much easier to scale up, and it's much easier to customize things. On the other hand side, on the Python implementation, it was easier to use. Comes with more limitation around visibility. For example, the validation loss not visible. We couldn't use a GPU and so on. So for the long term, we try to stick to TensorFlow, but this one model, for time constraint, we started with version 1 in Python. So MLflow, what is nice, we can track everything we like out of an experiment, and we can compare them together, see what was beneficial, what was not, track all metrics, but also we go the next step and we try to track plots. So what we try to do within our pipeline is also to visualize data as much as possible, automating all of the visualization such that retraining a data set results into regenerating all plots. We use sub-brands on MLflow to log also every trial from hyperparameter tuning. So then we can see what worked, what didn't work, and we can discuss it together within data scientists. About data, we have a data engineer in the team. He is dedicated to ensuring data quality is there for the data scientists to build models on top. He uses a tool called DBT. DBT is doing what you see in the picture. We have raw data, they are clean, they are not clean. And there is a bunch of SQL statements implemented to make this data from raw to data set ready for machine learning. All of this is tested and documented. So he is constantly trying to improve this model. It's a data model that works per events when we look at online data. And he did a great job at, allowing us a clean environment to cook, let's say. And but despite that, still, despite our best effort, we see a lot of data weirdness in the process. That's why we always try to do smart pre-processing, not only done for the sake of doing it. For example, duplication is ensured by the DBT model, but still we found sessions of repeated articles that are there many times, and this is obviously not making any sense. Or we remove single item sessions within a pre-processing component. And then we also visualize how much are we filtering out of our data set, and we track it with MLflow. We do temporal data set split, and the reason here is, so we train on 1 year more or less, because looking backwards, more than 1 year meant for us data quality was not sufficient. We split temporal because we want our test data set to be as close to production data as possible. In the end, we don't have to forget, the test data set is our estimate, how real world data will be distributed, and all the metrics we score them on the test data set. So if the data set is not real enough, we risk doing completely wrong assumptions. Within our pipelines, we try to visualize as much as we can. There are these HTML artifacts that are possible in Vertex AI. By clicking on the artifact, you see custom plots, so simple counts. We check for session data if there is anything missing, and we inspect them at time when things start to look weird, especially in terms of metrics. What are metrics, and how do we evaluate that quality is good? This is very tricky, and again, in one of the papers I linked at the end, it's very well explained. It's very hard to evaluate recommendation systems. They come with an extra challenge that is not there for other machine learning models or problems, which is what we typically do is what we are trying to predict is a user action, or maybe the next item in a basket, but that's not what we hope to see in production. The best recommender systems are a trade-off between exploration and exploitation. We want to inspire people as well. We don't want to always recommend something that they already know. This would be a useless recommender system. We don't want to predict exactly what they would do anyways. And that's very hard to do because it's a mismatch of concept between what we hope to see and what we train a model on. So how to mitigate this issue? It's very hard. There are some ways of doing it, but like uplift-based models and so on. But for this kind of problem we have at hand, that was there. This problem was there. We are aware of it. We are not mastering this skill 100%. what we do to mitigate the problem. We have different sets of metrics. We have the machine learning metrics within our pipeline. So we split the data set into test, train, validation, and then we score on the test data set. Okay, this is your assumption, or our assumption. How well will we do in production? But in production, we have different metrics: click-through rates, purchase-through rate, revenue uplift. Now we have a key driver metric for A/B testing, and we have a key driver metric for machine learning. In our case, it's NDCG at 5. We try to monitor both metrics and to collect the history of those. And this is one of my learnings that I gathered during this time, but I will say one more word about it in a minute. Whenever possible, we also A/B test. A/B testing is done by splitting users, or per session or per users, at random. A group will see a version of our algorithm or a variation of it, and the second group will see something else. And then we measure whether there is statistical difference between these two groups. And we roll out to production whenever we are happy with the final metric, which is a business metric again. So the NDCG at 5, this is a ranking metric. We like it because it also accounts for order. We want that relevant products are also showing up in the beginning. Okay, so we work for more than 6 months at this project. The data scientists build the pipeline, and you know, all of the technical implementation challenges that are always there. Coding reviews, we did a lot of experiments, we did a lot of comparisons. We were lacking a good evaluation framework that took a long time to do. We had some hard challenges on the way. But now at this time, how do we go to our way to MasterChef? Like, this is okay, it was our cooking time. But what can make us master chefs at doing recommendation systems? I thought of the challenges as the spices for all of this. Like, to get the real flavor out of our recommendation system, we need to be good at using the spices. Spices are, to me, are learnings. And I wanted to gather 3 of the most important ones, but definitely there are more. My first one, key takeaway, is do exploration in automation. This was so important to do in our scenario because, you know, you leave university, they teach you need to do exploratory data analysis in the beginning of any machine learning project. And that's what we did. So we had a Jupyter notebook, classic way of doing it. We had our toy data set, it was a sample, then it was a full data set, and we tried to explore what's in it. But why do we have to do a standalone analysis when this is code, right? And we can just put it into the pipeline as a component and regenerate these plots over and over. We do it within our input data sets. We do it after pre-processing to measure how much we are losing. Where are we losing data? So is there a category that is particularly affected? We repeat this also on the recommendation. So we want to know statistics around what we are recommending. And this kind of data analysis, they are so powerful because when you have a system up and running and you have to monitor quality, this is incredibly hard to do. You are focusing your attention on a different problem, and now there is, I don't know, a click-through rate going to 0, and we have to investigate why. It's very easy to go back to the pipeline, click on a link and see this plot. Oh, wait, data is not even there. And this I experienced in the first place. I saw myself the case of a model which was running all green in the pipeline, but data was not even there. So definitely we were bad at logging, definitely, but how do you debug data? This is not something so trivial to do. So this very simple basic plot helped us spot a lot of data related issues. And we started a conversation with the data engineer and point him towards more tests that could be incorporated into the DBT model. Talking to the data analyst on the other hand side, she had built a great dashboard around online data. We try to align that same analysis, have it into the pipeline for our model who is running, and our real world data. We want that data is distributed as closely as possible. The developer's baseline. This is one of my favorite learning because I was a junior data scientist. I left university and I learned a baseline model is important, is fundamental. It's a simple model by definition, and you want to benchmark your model against the baseline, right? We all know that. But then what is a good baseline? We read into papers that you have to implement a popularity-based baseline. So this is like you get some articles that are popular and you recommend them. This is the popularity-based baseline. Or a random baseline even, you sample at random and these are the recommendations. Okay, all makes sense. They are even in published research, but then you ask yourself, do they make sense? And I tell you, most of the cases, I don't know, for us, they don't make sense. The popularity-based baseline reinforces the popularity bias problem even more. So we would say that it's best for the model to be good at popular item even more than it already is. And what about the other articles? They are also important. The other baseline, the random one, is too easy to beat. For an assortment of 90,000 articles in Germany, this is a probability of 1 divided by 90,000 to extract a good alternative. So it doesn't make any sense. What we do in my team is we tell ourselves, if I was a software developer and I don't have the chance or the possibility to use machine learning, how would I solve this problem? This is the developer baseline. This is what you would do. And to us, we told ourselves, if I was a software developer and I cannot use machine learning, I would sample from the subcategory. So a user is viewing an apple, and I sample at random 10 apples, and these are 10 recommendations. At least it's smarter than sampling at random overall, right? And it can be even tricky to beat for some kind of machine learning model. But if we are not better than the developer baseline, there is no point moving to production. And the further benefit out of this is the developer baseline can be pushed to production. So for the long term, what we want to have is a quality gate within our pipelines. You compare the baseline to the model, but if the model is not good enough, it's not beneficial to push it. So maybe it's good to push the baseline instead, or maybe an older model, but this is another topic. The third one I stole from a paper on MLOps that is from Google. It's linked at the end of the presentation. It's called the ML test score. The authors come up with quality tests around model that we can do to ensure the quality stays over time when we are in production. And I like it because it applies very well in the context of recommendation, as we have this problem of mismatch, right? We want to predict the next item, but then we hope that it results in a good recommendation system. So we monitor very, very closely the history of online metrics, the history of offline metrics, but then we need to put them, they need to have some kind of relation. They shouldn't be completely unrelated. Now I will be honest with you. We are far away from that, identifying this relation, identifying our best perfect metric that correlates or relates to the metrics that we see online. That's incredibly hard to do, but collecting metadata is something we are working on, and we are on a good track, I would say. Okay, enough for the talking, enough for the for talking about the history. It's time to see some results. So like I said, we start from the machine learning on the test data set, so the standard way. On a country, this is Germany, we compare the model to the baseline, and we see that we achieve better performance on all metrics. This was the best we could do. We did a lot of experiments. Our reference metrics is here, NDCG at 5, so normalized discounted cumulative gain at 5. So it means by looking at the top 5. But anyways, also for other metrics, we are better than the baseline by far. And we also score separately the long tail. So this is the long tail. It's articles that nobody buys, but there are so many of them. Why we do it? Because we compared MetaProt2Vec and Prot2Vec. We wanted to confirm the assumption that quality gets better for those products. And this really happened because Prot2Vec was very bad on this long tail, like we assumed. So the use of these features, of the meta features, the brand, the category, subcategory, really is helping quality for all of those long tail products. That's what we see. So we were happy, but this is again just a something we are hoping, right? Like you don't know what will happen when we go to production. So we had then an intermediate phase between the scientists saying we are ready and the engineers saying we A/B test. We wanted to do some check in the middle because like I said in the beginning, do you remember coverage? There was also latency. There was also some engineering metrics we have to keep in mind. So we thought about a what if analysis. what the engineer did is mirroring traffic from production, which was going to the juice query commander, to the new hypothetical version that the data scientist thought might be working. So we had data that looked like real traffic from real users, what is people viewing, what the current system is recommending, and what the new one would theoretically do. So what we are missing is the clicks. We don't know because the model is not live yet, but it gives us a good understanding of quality. It helps us do refinements from the machine learning side, and it allows us to track some performance metrics like coverage. We measure an improvement on average by 45%. So yes, Metro.digital helped improve coverage by far. Remember, it was at 40%. So this is an improvement of 45%, which means for a lot of countries, we go to the 90% area. So a lot of products now have alternatives. Quality is sufficient. This is very hard to estimate because, okay, the metrics we have offline say that. Is it really true? What we do is intensive checks manually, which is very boring, but it's very important because no chef can be a good chef if he doesn't taste the food. And us as data scientists cannot be good if we don't learn from our data what's there. So what we do is typically do the boring job, output the recommendation, look at the product, do they make sense? We vote on it, we discuss it, we look at slices of data. And by the way, quality of slices is also one good idea to measure the quality is sufficient on every piece of the assortment. This was also what us stakeholders liked, that we conducted data analysis specific to group of products which are important. So for example, products that go out of stock very frequently. We extract them at random, we sit together, we check if they are good enough. But also we do some kind of data analysis that looks like how many times is the brand matching? How many times is the category, the subcategory matching? How many features are actually matching from the most important ones? This is not 100% scientific, but it's still giving us a very good indication. This what if analysis is there also for the bad models. There was some countries where we are particularly bad with quality. We intentionally gave the engineers a bad model because we wanted to see if it's really bad. Maybe it was not, right? And that's why we did it. After this phase, there is a refinement, again, going backwards to the latest point in time improvements before A/B testing. However, it's not even sure we will A/B test because the coverage improve is so great and the quality also seemed much, much better on the first shot that we consider not to do it. So this is now ongoing and I cannot give you more than this. So I fortunately cannot tell you about A/B testing results for this model. But okay, the time was out for the project. We checked the requirements. We achieved flexibility and quality. Quality was judged by our stakeholders and ourselves qualitatively by a data analysis on this what-if analysis we did and by looking at the metrics on the test data set. Low latency, yes, it was respecting the threshold that was given to us of 100 milliseconds. Coverage, yes, improved for all countries by far. And automation also reached because the pipeline was built by the data scientist. Still needs improvement. It's not perfect, but those improvements we will do on the way. The only requirements we missed is the, oops. The only requirements we missed was, cooking time of 6 months. The project lasted more than this, unfortunately. Unpredicted how much time you can need for such a project. We had to learn how to use the Vertex AI tool. We had some turnover of people and all of the fun, unexpected things that happen in any project in the real world. But okay, enough for this. I have prepared a small demo to show you how we do the quality checks and some interesting insights that we discovered. And so I have uploaded those vectors we spoke about into this tool, which is called TensorFlow Embedding Projector. This is an open source tool, accessible to everybody. It comes with a preloaded tensors, so vectors, from the Word2Vec, but this is not what I'm showing to you. I have uploaded our real embedding vectors that come from training for the Germany dataset. Every dot here represents an article, and the tool, what is it doing is only visualization. The calculation of similarity scores come from my team. If I scroll with the mouse, you see names. This is every dot here is a product, and it corresponds of a vector of side 128. You see it from here. And I have 96,000 products in the visualization here. I color differently food and non-food. So that's what the colors are representing. And I can also stop the visualization and explore. You can scroll in and out. It is a really cool tool. But what is nice is I can click on random dot and see what the product is. So I don't know, this is now random completely. It's very hard sometimes to understand what the product is. Remember I said how bad the text, how bad text looks like at my company. We try to concatenate it with as much information I could find to understand around the product, but these are not all the features that we used for training. F, for example, means this food is in a carton. I don't know what this is, honestly. It's a juice, looks like a juice. And now to the right side, what you see is what our machine learning model think could be a good alternative to it. And it's also juice for most of the cases, I think. Also, my German is a little bit limited. I can also scroll on more points and repeat the same, another juice here, and one I think means the quantity. By the way, MW is the brand because our naming, that's how it works usually. So all is 1 liter and it's all fruit juice, yeah, juice. Okay, I could do this for all products and spend a lot of time, but I want to jump through obviously it doesn't work always perfect. I want to show an interesting example of lactose-free, because this is like products that I know from collaborative filtering this is a benefit of having collaborative filtering as a recommender system. You let data tell you what is a good alternative at the eyes of the consumer. Remember that. Lactose-free is something we don't have a category for in my company. So we are not able to easily select lactose-free. And the text is not helping us. By the way, the algorithm doesn't use any text at all, because sometimes you spell it differently than others. Sometimes you use this LAC abbreviation. Here I see, what is this, lactose-free yogurt, and it's very good. I think here alternatives are really good because the first one is in the same quantity, but different percentage of fat. And the next 4 are in different quantity, but same percentage of fat. And then, okay, it starts to go a little bit different later on, but it's all lactose-free. Why? Because people who consume lactose-free are similar to each other, and they interact with articles that are lactose-free also similarly to each other. And if I would be doing machine learning without collaborative filtering, I would not be able to find any feature for lactose-free. The same I see for tofu, same story. I go to a tofu and I see, yeah, it's even wrongly classified. If you see here, it's said to be sausage, but this is tofu. It's 2 kilo bio tofu, and there is no category for bio, there is no category for tofu in assortment. So using data that come from user behavior data help us understand that the best one is also tofu, the best replacement, and first the top 5 are tofu. Then here is the point where we have nothing else in assortment at the position 5. It comes to pick on Wurst, which is vegan, and other vegan products. Why? Because again, it's a particular group of people who interact with this product in a similar way. And the same we see for baby food, because it's parents buying for the kids usually. So this is like where I like it very much, still with some limitation. Like you can see here, vegan Fleischwurst, like this is sausage and vegan, is not a good replacement for tofu. Definitely we are aware of it. Here it's about sacrificing coverage in favor of quality. And it's a hard choice to do, because where is the cutoff for this? All of these are big challenges. We didn't solve it, I'll be honest with you. Again, this is just the version 1 of our alternative-based machine learning algorithm. And we want to have iterations on top where we refine our results and identify better combinations. And together with the data scientists, my great colleagues that are in my team, we hope to do better than this. And I am almost heading to the conclusion. I have just a few more slides to show. Now that we got a bite, I need to tell you something about God. I actually wanted to show you our cooking courses, where I found the information I mentioned overall, our presentation. The ML test score was really interesting. I recommend it to everybody doing MLOps, but I'm also sure that many of you already know it. Measuring the business value of recommender systems, like here is discussed, a lot of discussion around what are good metrics, and this is always very important and still unanswered for the majority of it. And the 3 papers that are here. Okay, so the next time you will be there sitting in a cafe, drinking coffee, and you want to buy your favorite mixer, which is unfortunately out of stock. Let our recommendation system drive you through the best replacements. You will discover a new mixer that you didn't even know existed. You will become a great cook, just like me, being a data scientist, learning from recommendation systems all the time, learning through machine learning. I hope the more I experience with this area, which is so interesting, the more I will learn and become myself, like you, a better cook. And I'm heading to the end, so I will ask you if you have any questions. I will be happy to answer. I hope I didn't lose so many people on the way. I'm going to head to the microphone to Dimitri.
Yes, thank you for this very interesting presentation and share how you cook your recommendation system. We have several questions. I will share my screen also, but as I see, we have several questions from Paolo, but maybe he will join us and we will discuss him questions and if you want.
Sure, no problem.
Great.
Okay, actually, I had 2 questions. I posted them in the chat as well, but I can just read them. So my first one was about your idea with the Word2Vec to translate your products into vectors. And I was wondering, have you guys also tried transformers, since they're known to be quite well in quite good in this approach, and then just apply the same similarity in your recommendations?
Okay, thank you very much for the question. And I see from your question that you are very familiar with the area. I'm very happy to know you. Your idea is a really good idea, and definitely that's great for the next improvement version on top of this one. We didn't try it, and the reason is we had a limited amount of time for experimentation. We always try to stay within deadlines, and we know that the faster we go to production, the easier it is to get feedback data out of real users, you know? So that's why we went with this approach, because it was easier to implement than transformers, at least we thought. From Word2Vec, we went to the Metro.digital approach again, because it was easy to switch from one to the other, and it was fitting very well with the tech stack. However, we want to continually improve on top. It will be definitely interesting to try out transformers, and yeah, great that you are mentioning it. For our version 2, I really hope to get there, to get to do it. The team also focuses on more recommendation systems. Some, they are not all alternative based. We have also personalized recommendation systems. We also have one that is used for marketing campaigns, and we have limited capability within the team. So we don't have this possibility to always spend a lot of time doing the experimentation like we would like to, but definitely it's good. And thank you for proposing it. Also very nice to meet you.
Thanks a lot. Thank you for answering the questions.
Yeah, you have also second question about.
Yeah, I think Dora also addressed it in the same way. I guess it's, from what I understood, it's for quicker experimentation, right? So you just want to have in the end one vector for one item representing the product.
Yeah.
Good. We also see that Ricardo wants to ask the questions, as I understand. So you can ask. Yeah.
Yeah. Can you hear me?
Yes.
Yes.
Okay. Thank you, Dora, for your talk. I really appreciate the fact that you go all over the process from getting the data to production. But here I have a question about the input of the model, because in recommender system, one can focus on the products or one can focus on the customer. So in your case, you focus on the products and then you get in the latent space, the representation of the products. But what about instead focusing on the customers and maybe get a latent space of the customer? I'm asking it because where I work, it is a bank, we have obviously know all the kind of customer that could be interested in clustering or categorize it. And okay, I just let you answer.
Great question. Thank you very much for the question. And I'm also happy that you are working with a similar problem. I come in with a vector space and so on, or something similar applied to a different context. Definitely, we are using only products, that's true, because this is not a personalized algorithm. So that's the bit of it. We consider user sessions and we don't make any distinction, but we have personalized algorithm in production, which is merely based on the matrix factorization. And in that case, what you get out of it is exactly what you are mentioning. You get at the same time out of one algorithm training, both the customer embeddings and the product embeddings. This is one way, one possibility. Doesn't, obviously, I'm not recommending you to use it because it always depends on the problem at hand. However, in that case, you always get a vector for every customer, and you can also measure customer similarity, and you can also, that's how we, recommendations are personalized then for every customer, but you can also relate a customer to any other customer, try to cluster them, try to identify interesting relations. That's definitely possible with customer embeddings. Another approach I have seen, that was a talk at Strata conference I attended. This was for a problem in where data scientist also was using embeddings. She derived the customer embeddings out of the product embeddings via averaging, so simply via averaging. She also showcased the results and it seemed impressive, at least it seemed. So I know that at least at another, in that scenario, that's how the authors did it. When I researched into how to derive customer embeddings, I myself found that it's a common approach to average products. So if I am a customer and I am buying, I don't know, a basket of 100 products and I have a vector for each one of them, the average of them is a customer embedding. I've seen this done. I cannot tell you whether this is a good idea or not. Depends on your case, depends on your data, depends on the scenario. The other possibility I've seen in my personal experience is matrix factorization. Out of a matrix factorization, you get it kind of for free. You train an algorithm and you get two matrices, one for products, one for customers at once. So this may be another possibility.
Nice, thank you. It's a simple idea and can be really impactful. And if I may, the second question very briefly, for the product, I want a latent space of the product and then I see the co-occurrence with the others, but we are in a problem that is binary. It's not a regression. For example, it's not the cost of that product or how many of the other product you build. The similarity was only if there is another product of that, not like estimating how many other products are suggested. It's like a recommender system for binary information, not, for example, how much a policy I want to sell you, or how do you want to invest on a financial product.
Okay, I'm not 100% sure that I understand the question. I try to rephrase it, but please tell me if I didn't get it. You are saying that in my scenario, this is not a binary problem, and in your scenario, it may be. Is it right? So you say in your case, you have a data science problem at hand where you have a binary labels. So where 1 means yes, 0 means no. Is it correct what I understood?
I mean, in my case, a customer can buy a product, putting it, I don't know, 1,000 euro, 2,000 euro to buy that product, and you have a scalar value. In your case, the suggest is only one product, is that product. You don't estimate how many of that product
okay, I get it. Yeah, what you are mentioning we did for another recommender system, because in that case we have customers and products, so we want to account for what every customer is interacting with, how customers are interacting with the products. So for this other recommender system, we A/B tested, in fact, the 2 scenarios you are mentioning. In one case, binary. So did the customer ever interacted with the product in a certain amount of time? And in the second scenario, we had scalar values. So for example, a customer bought 100 units of a certain product. And now that's, like you say, not anymore binary. So we applied a logarithm transformation on top. And we A/B tested these 2 scenarios. It was same algorithm. In one situation, we had a binary label, binary labeling setup. And in the second one, we are considering the logarithm of spend, of customer spend into that product. And for this A/B test, what we learned is that most of the time it was beneficial to do option 2. So to give the model also more information, but not always. So for some countries, we discovered that it was better to stay binary. So,
okay.
Yeah,
okay,
but
okay.
this is applied to us. So for your scenario, I don't know. But this was, again, a matrix factorization where simply you can imagine customers on the rows, products on the columns, and it's inside every product item combination was either a number or not, or a 1, 0. But in this particular scenario of the recommender system I have, there is no customers. Labels are done, like 1 is automatically inferred from coview, and -1, like the negative label is inferred at random. It's sampling at random. So there is negative sampling in the, I didn't mention it in the presentation. Yeah, thank you for the question. You remember me that I forgot something, to say something important.
Thank you very much, Dora.
You're welcome.
We have also a question from M. So he write the question, but maybe he want to ask, as he up the hand, the question about A/B testing.
Hi, Dora. Can you hear me?
Yes.
Thank you so much. It was a great talk. I work on the marketing side, so I'm very curious about the A/B tests that you ran, because you did mention about it. So I'm curious about the learnings that you had, and if you can share an example of how you chose, yeah, that would be great. Thank you.
You're welcome. Thank you for the question. Very interesting. Yes, we've been A/B testing intensively for about a year on a different algorithm, where our reference metric was click-through rate. We had several learnings around it. By the way, we did Bayesian A/B testing. That's how it was implemented. We splitted user sessions that are on product detail pages into groups, where one group would see a version and the other 50% would see a different version, let the A/B test running until statistical significance, and then roll out to the whole country the version that increases the metric. However, the learnings out of it. We started with click-through rate because it was easy to calculate. That's just the number of clicks divided by the number of impressions. That's straightforward, intuitive, but it doesn't really measure quality of recommendation system. This is very well dealt with in the paper I linked. There are different metrics which look at the long term, which are more beneficial, because click-through rate measure only user attention. It doesn't measure quality. Revenue metrics might be a better idea, and it's what we are trying to do, especially because business people is always interested in the revenue coming from recommendation, and they talk money most of the time. This is where we are heading for, and we are hoping to switch a key metric from click-through rate to purchase-through rate. We A/B tested several things. We A/B tested versions of the same algorithm with different variations, like this one with the log spend. We also A/B tested different algorithms together, different implementation even. So for example, two libraries, two different implementation. That's out of the learnings. The most impactful A/B test we ever run in a year was very surprising because it was not machine learning related what we had done. What we tried to do is we observed that embedding dimension was having an impact on click-through rate. And so we tried to change the size and test it again. So imagine in version 1, we have small vectors, and in version 2, we had big vectors. And the quality was impressively different. And that's just because the embedding dimension was smaller. Here is where we started to think, okay, maybe actually that's because of latency. And this is why I said in the beginning that latency was the most impactful A/B tests we had done. Yes, so the recommendations were slower, and that's why they were worst. So even with the same algorithm in comparison, another A/B test we did to confirm this hypothesis was we delivered less recommendations, and this also increased the click-through rate. So that meant the recommendations again were faster for the second time. Just by reducing the length of this list that was delivered via the API, we got better results in A/B testing. So we learned the importance of latency out of these two A/B tests. Later on, by searching around on the internet, I found a lot of blog posts, articles around this problem. So it's very well known how much latency can contribute to the results of an A/B test. And this is also why it's important to monitor technical metrics and the business metric together, like to have them visualized together. I hope it answers the question.
Yes, it does. Thank you. Thank you.
Yeah, thank you. We have more questions from Evgeny about retraining model. You will ask, or? Okay, so how often do you retrain your embedded model? Do you aim for high CTR or some kind of long-term customer value?
Very good question. Also, I see from the question that the person is very, very much familiar with the embedding world and machine learning in general. So, like I mentioned, the algorithm suffers from cold start. So, I mean, the straightforward way is to retrain frequently so that new products are popping up for which we have an embedding. However, there is an alternative way, which is a little more accurate. Like when you look out there in the MLOps way of doing things, correct? In theory, model training should be redone when the data is drifting. So what does it mean? That the distribution of data in train is not real anymore. This is the time to retrain. This is well explained in many of the MLOps papers I've seen. So you train your model on something now, I don't know, you have 1 year of data, now something happens in the next 2 years, Corona starts, and data is distributed completely different. So you train the model on a data set that is not real anymore. This is the time to retrain. And how to spot that? Very often, there are some drift detector models that are being used within machine learning pipelines to identify this moment of retrain, but that's very, very advanced. And we are not there yet. Like we don't do this. We retrain at need based on the problem at hand. For example, for another algorithm we have in production, we train every 2 weeks because we used embeddings also for personalizing some marketing campaigns at a certain point. And the marketing campaign was renewed every 2 weeks. And without retraining, it would be impossible to get different vectors. So that's why for other countries where the recommendations are just there up and running and traffic is very low anyways, we had even retraining every month. But I would be honest with you, we didn't do anything fancy around the retraining so far. And we have it in our roadmap to start to do MLOps a little bit better, investing a little more time, and yeah, just to do things right.
Good. And one question from Evgeny. Do you use some kind of vector database for distance calculation? Do you calculate the night boards or calculate them in online manner?
Yeah. Also, very good question. We need to consider for what the user is viewing at the moment for us to be able to retrieve vectors and give it to them. And for the other recommendation system that is running, we also need to know the customer ID, because if the customer is logged in, for example, we need to retrieve from their ID a different vector. So we had to face this problem already for the previous recommender system, which is using also the customer. So we needed to process the information. A customer is logged in and is viewing a certain product, and now this vector have to be around the given product. So for that reason, the engineers investigated different possible possible tools for doing this, and they decided for Elasticsearch. However, I can tell you, so Elasticsearch, what it's doing is mapping to the pre-calculated vectors. Yes, it's like taking the vector for a given product, matching it to every other ones, calculating cosine similarity, returning until like, yes, they are pre-calculated, but they are also updated. So at every retrain, vectors are changing. We are moving away from this way of serving. Still, this is a part of a large investigation that the engineers are doing. We are considering to wrap the cosine similarity calculation around the model, which gets containerized, and then we just request predictions to the model. This is one option. But we are also investigating matching engine, which is a Google side of the Vertex AI. I mean, somebody already did it in the past, and yeah, it's still in the air. Like, we don't know what to do with it. And the Seldon deployment. Seldon is the favorite way from our current tech lead to go forward with this one. So we are moving away from Elasticsearch. I wanted to tell you that. I am not the best person to give you the details. If you like, I can put you in contact with the best person, because I don't work actively on model serving. So that's how I can explain it to you. I hope it's sufficient.
Good, thanks. So I think we are a little out of time. So if we have more questions, let's continue discuss in the Slack. Please write on Slack your questions. We will answer you shortly. I want to say for Dora, thanks for joining us and for preparing so good presentation.